Imagine driving a car on a circular track at a high speed. The only thing keeping you from skidding off is the friction between the tires and the road. But what if suddenly that friction disappeared? Would you just slide off the track? Yes, you would, but if the tracks are banged, you will not. So, what is the secret? A regular road is flat, but a banked track is cleverly tilted at an angle, allowing cars to move even without friction. Let's try to understand how these tracks work in absence of friction. Now, when frictional force between the track and the tire is absent, the centripetal force contribution from the frictional force would be zero. But then, for the car to move in a circle, there has to be a force that pulls the car towards the center, or in other words, provides the required centripetal force. So, what happens with these tracks is that because the road is tilted at an angle, the normal force has two components, one horizontal like this and one vertical like this. And here you can see that the horizontal component is pointing towards the center quite the way a frictional force would, and therefore this provides the necessary centripetal force for the car to maintain circular motion. And we can also see that the vertical component is balancing the car's weight. So we can say n cos alpha is equal to mg. So with this information, we can write the F is equal to ma equation for this car as follows. On the left hand side, we have the net force acting towards the center as n sine alpha, and this should equal the product of mass of the car and acceleration. And we know that acceleration is centripetal and is written as v square upon r, where v is the car's velocity and r is the radius the turning curve makes. Now, if we write n in this equation as mg upon cos alpha and substitute it in this equation, what we get is mg upon cos alpha into sine alpha is equal to mv square upon r, or tan alpha is equal to v square upon g into r. And if you want to, you can write alpha as tan inverse of v square upon gr. Also, you can write velocity v as v is equal to root of gr times tan alpha. Now, what I have seen is that the students often interpret these equations incorrectly. So, this is the way you should understand these equations. You can see that for a given angle alpha, the horizontal component that is providing the centripetal force becomes a constant because n is a constant and alpha is also a constant. So, this expression is fixed. And since this is the force that is providing the centripetal force to prevent the car from sliding away, it kind of puts a cap on the measure of maximum velocity that you can go up to. That is, for a given value of this centripetal force, there is a corresponding velocity on the right hand side that will give you this equality. And if you go beyond that velocity, this centripetal force will not be able to keep the car on track. That is, you will need more centripetal force if you wish to speed further. So, let us say the roadway authorities put a sign that on a particular stretch of road where friction is almost zero, let us say due to ice, you cannot go beyond 25 meters per second. Then that means they would have banked the track to enable this velocity limit. So if the radius here is 230 meters, let us say, then the banking angle can be calculated using this formula, and it works out to be approximately 15 degrees. In other words, if you are on a track that curves such that the radius is 230 meters and the angle of banking is 15 degrees, then you just cannot afford to move at any speed more than 25 meters per second. And if you wish to move at a high velocity, you will have to convince the highway authorities to increase the angle of banking so that you get more horizontal component and therefore more centripetal force to keep you on track at that increased speed. And one interesting thing you can observe here is that this velocity is independent of mass of the body. So I'd suggest you head over to this playlist to get deeper insights into this topic, particularly circular motion. And if you like the lesson, do leave a comment or give it a thumbs up. It'll be quite helpful, and I'll see you in the next video.